you should be getting the hang of how to count up all the number of electrons you have, and then make sure you start between the atoms for covalent compounds, and make sure everybody gets 8. That's what you're trying. That's called the octet rule. If you have extra, you can put them on the center, and that'll just overload the center. If you don't have quite enough, you can just steal some from one and just make a double bond or a triple bond, and those are the 2 tricks that you have. But once you've got the hang of drawing these, then you can start to understand what shape they have. And the reason is because those bonding electrons that are between those atoms, they are electric. They're negative charged, and they don't like any one of those lines doesn't like another one. And they'll repel each other as far away as possible. So there's a theory called the valence shell, electron pair repulsion, if you know what those bonding pairs look like and what direction they're pairs, because every line is 2 electrons, right? If you know how many they're coming off of an atom, you'll know that they'll orient each other to get as far away as possible from each other. Okay, that's because they're both negatives. So the first thing you have to do when you're going to determine the shape of a molecule, you're going to literally be able to determine what shape these things are, is to draw the Lewis structure, those line structures. Next, count how many lines are off of the center atom. How many bonds does it have? And once you know that, you're going to use this chart down below us to figure out what shape it looks like. So let's think about this. If you have a compound like carbon dioxide, okay, that's the first one we'll take a look at. Actually, let's look at hydrogen first, because that's the very simplest. Okay, hydrogen has 1 electron each. They'll share an electron between them. So that is a case where there is 1 pair of electrons coming off of an atom. What is the shape of that? Well, it's pointed towards the other atom, so it's linear. Okay, that's sort of a default one that just makes sense. Okay, it's an s orbital that's being here. Remember, if the s orbital is the sphere here, and here's the sphere there, they look like that, and they end up having an orbital that ties them together. The electron can travel around these. It ends up looking something, probably something like, okay, this, where the electron's path now merges into something like that. It's 2 s orbitals. Okay, that's what I'm talking about being linear shaped. Now, that's the first one. Let's take a look at where there's 2 groups coming off the center of the atom, and that might be more like carbon dioxide. Okay, carbon dioxide right here has that electron Lewis structure to it. The center atom has 2 groups coming off of it. One group going to an oxygen, and the other group going to that same oxygen. And so what ways are they going to try to avoid each other the most possible? If one heads this way, the other's going to head exactly opposite. And it should look something when we usually show these molecules like this. Those groups are heading as far opposite each other as they can. So that's a linear molecule. It's in a line because 2 groups want to get as far away from each other as they can in that shape. So that's what's going to be called linear. Now, we don't have an orbital that points one direction and an orbital that points in the opposite direction. What we have are S's, remember? And we have P's, which look like this. They actually point either all around or they point in both directions like that P orbital does. So we're going to have to hybridize them. In other words, we're going to have to cut them up and re-add these together somehow into a hybrid orbital, sort of Frankenstein-y. And I'm going to take, for instance, let's say I'll take just this half of this sphere and put it together with that half of that P orbital so that it becomes an orbital that looks like this. Okay? And what if I take the other half and mix that with this part, and it ends up looking more like this? Okay? This then would be the S combined with half of the P. And this would be the other half of the S and P orbital. So they become what's called an sp orbital. Basically, you don't have to worry about how that process happens. Just think you throw them into the blender, and then I need 2 orbitals. And you know what direction they're going to point opposite each other because 2 things of negative charge are opposite. So you don't have to worry about what process this goes through, but that's what's happening to these orbitals. You're taking the old atomic orbitals and making molecular ones. Okay? And when there's 2 of them, it's going to be S and P because that's how many you need. 1 SP going that way, 1 SP coming back this direction. That's an SP, that's an SP. Now, let's take a trigonal example. What happens if you put another group on here? Let's take this one like this, and I'm going to put another group right into here. Well, when you do that, the way that these things can best avoid each other is these 2 are going to start to bend downwards, like my fingers, and this one's going to join in, and so you're going to get to, like I said, this is the newcomer comes in like this, that bends these 2 down, and this ends up becoming this shape, triangular planar. Okay, it's a plane, but it's got 3 features in there, and a molecule like this could be something like the nitrate polyatomic ion. That's got a -1. So when you do the electron dot structures for this, it ends up looking like this. And we usually put a big bracket around there to take care of that extra -1 charge. Okay, we don't know where it ends up. It's just in there as a group. But that's what that looks like. And if you look, the nitrogen's got 3 sticks coming off, a double bond, a single bond, and a single bond. And so it's going to then be in that shape that we've already said. The best way for 3 things to get away from each other is to look like that. That's going to be called trigonal planar. And that actually, I should put the word planar because there are other kinds of trigonal. I'll make sure that that's included in the notes. That's a plane that has 3 things getting far as we can apart from each other. You know, sort of like, you know, like this, you know, that kind of a look. Okay? What about 4 groups? Well, a good example of 4 groups coming in. What's going to happen when I put a 4th group on here? Put another bond in there. That's going to cause those 3 atoms here to droop downwards, like my fingers. Okay? And that's going to then end up looking like this. Notice how these all have bent downwards. That's called trigonal tetrahedral. Let's clean that up. Okay, tetrahedral is a good example of what CH4 ends up looking like. Each one of those has 1. Carbon has 4, so it ends up looking like this. I'll give it some perception of the way it looks like just by the way I draw it. Okay, the best way those 4 get together is just like if you take the first 3 fingers and your wrist, like you're doing a 3-fingered push-up, it would end up looking something like that. Okay, that'd be your own personal example, but it does end up looking something like this, like a little pyramid. Okay, that is tetrahedral. Now, what happens if I put a 5th group on and you notice that the center atom has 5 groups coming off it, and you put it like this? That's going to cause these guys to then go back into a plane like this. Notice these are flat again. This is called trigonal bipyramid. It looks like a space station or something like that, or a JAX or something. And so that is trigonal bipyramid. Something like those are going to be something, oops, let's skip into that guy. Here, let's do it fast. Delete, clear ink. Phosphorus hexachloride. Ends up being a phosphorus in the middle with 6 chlorines around it. Each of the chlorines has their full complement when it's drawn right. Should look like that. Okay, but that center atom looks like this, so that all 5 of those groups are as far away from each other as possible. 3 of them are in the trigonal planar, and then you got a top and a bottom. So that's trigonal bipyramid, 2 pyramids on top of a triangle. Trigonal bipyramid. Now the last one is you're looking at that trigonal bipyramid. What if I put a group in right here? That's going to cause these guys to go straight from each other. And this one does look like the JAX, if you played with. It looks like the X, Y, and Z axis. And that's called octahedral. Octahedral is when a compound is, let's go xenon tetrafluoride. And xenon tetrafluoride, actually, when you draw that out, xenon goes in the middle. There's fluorofluorines around out here. The trouble is, after you've drawn these, that you've still got 4 extra electrons, and so you have to put 2 more on there. Okay, and that has 6 groups coming off the center, and that 6 groups then looks like we saw here. Okay, is octahedral. So what I want you to do is go back through all of those problems you've done, and you want to look at the center atom, just the center atom, and determine the shape of those, if you would. Thanks.